So this that means we can find, so in order to establish this theorem, then we need to show that try to construct this particular sub-semigroup of Tx and show that S is isomorphic to it. In other words, we should try to define this mapping here, psi, so that psi is a homomorphism, as in is one-to-one homomorphism. And by doing that, we have shown that S is isomorphic to the image here, psi of S. And this is what we are going to try to do. So this particular theorem gives the full transformation semigroup a kind of universal property, in the sense that there is a copy of every semigroup whatsoever inside the full transformation semigroup. And this theorem is very powerful in the sense that it is suggesting that we can drop studying any semigroup and concentrate only on the full transformation semigroup. That if we concentrate on the full transformation semigroup, then we can achieve the study of every other semigroup. Because when two semigroups are isomorphic, generally in mathematics, if you say two algebraic structures are isomorphic, then you are saying they are one and the same, algebraically speaking. As far as the algebraic properties under consideration are concerned, the two are one and the same, and so they are indistinguishable. So one is trying to look at this system, and it's a very difficult system with a lot of complex structures. One can just embed it inside Tx. So instead of concentrating on this particular semigroup that you may not fully understand, you can concentrate on the transformation semigroup whose element you are familiar with, and you are familiar with the binary operation. You can perform a lot of analysis here, and then via the inverse transformation, you translate whatever result you achieve from here into the corresponding result in the semigroup S. So this is it. Now we look at the proof of this particular theorem. The proof is actually similar to the one obtainable in group theory. So we choose a set X. We choose the set X to be the set, the semigroup itself, union identity. Well, this particular one is an extra element in one you bring, and we require that it should not be. So this is not belonging to this set. So the 1 shouldn't be an element of the semigroup. So we take an element 1 not in the semigroup and join it to the semigroup and then call that X. So X is chosen as this. And then we define for each element S a full transformation. So S alpha S. So there should be a subscript here, alpha S. So we define a full transformation alpha S from X to X by the following way. X alpha S should be XS. Well, because we choose our set to be the semigroup, so this is the semigroup multiplication here. If X is an element of the semigroup, so if it belongs to the semigroup, then you can perform the semigroup multiplication. Otherwise, if it is that extra element which you included was not there before, but you included it, 1 you call it, then you just say the image of X under this alpha S will be equal to S itself. And so therefore, with this, you can check that this relation hold, and this means it's a semigroup homomorphism. So which means the mapping sending every element of the semigroup S to alpha S, that is the transformation, the full transformation generated by S, is a semigroup homomorphism. From where? From the semigroup into the full transformation semigroup. And then one can also see that the semigroup is one-to-one, because if we assume alpha S equal to alpha T, then by the very definition of alpha S and alpha T, for every X, but well, by the assumption, since you assume they are the same, it means these things are mappings of a set. It means the result of the action of the map on any point would be the same. So if alpha S act on S, it will be the same as the result of the action of alpha T on X, because you say they are the same here. and because you are saying for all x, among element of x is 1, so I can choose 1, and then so which means if alpha s act on 1, it will be the same as the result of the action of alpha t on 1. So this is also true. But then by the very definition of our alpha s, when x is 1, it is just equal to s. So therefore alpha s, 1 alpha s is equal to s, and 1 alpha t would be equal to t. So which means if images are the same, the pre-images are also the same. So this mapping, this particular mapping here, psi, is a one-to-one map or injection. So therefore we have an injective homomorphism from the semigroup into the full transformation semigroup Tx. So this embeds S into Tx. So this is the universal property the semigroup is having. So this is the last part of my today's discussion. But before I round up, I will give you a few exercises. The first exercise is to consider a set of 12 elements, and then take this partial transformation and compute this composition of the partial transformation. So from the definition of composite, which we have described, try to find out what is alpha beta, beta alpha, alpha gamma, alpha delta, and gamma, where alpha, beta, gamma, and delta are given here. So just perform this composite, and then show that if the set X is countably infinite, and you take a subset of Tx to be the set of all full transformation for which the set X minus the image is still infinite, show that this particular set is a subsemigroup of Tx. So what you do is to take two maps from here, alpha and beta, and show that the composite is still satisfying this particular condition here. And then the third example, the third exercise, is to take the semigroup of natural numbers under addition and try to find an isomorphic copy of the semigroup. Remember the last theorem? We say every semigroup can be embedded in the full transformation semigroup. So I give you here the semigroup of natural numbers with respect to addition, and the task is to find an isomorphic copy of that particular semigroup of natural numbers into Tx, so the full transformation. So you try to find what that X is and which subsemigroup of Tx will be isomorphic to the semigroup of natural numbers. So this brings us to the end of this particular lecture. Thank you very much for being with me, and I hope to see you in the third lecture, where we continue our discussion on transformations of a set.